All right. So I think we're probably looking at the weather forecast. I think probably this week, most likely Thursday also quite a bit of forecast for snow. So I feel like it will also be remote. But let's see. Uh, so for today's class, so as you've seen, like our treatment of neural networks is it's different from a more applied course. Like our focus is more theoretical and mathematical. We want to make sure that we understand the mathematical and theoretical underpinnings of neural networks, which is why all the classes you've seen a lot of mathematical derivation on the board. So that's going to be a bit challenging. I think I have a reasonably approximate way of kind of deriving stuff uh, in an online manner. So we'll see how it goes, but it might mean that we'll kind of go a bit slow, and then maybe we will need to kind of make it up next week if we fall behind this week. So I think that's fine. We cannot control natural calamities, so we have to adjust to that. Okay. Uh, all right. So let's get started. First of all, uh, in terms of logistics, I think you have some assignments like quizzes and homeworks due, I think, end of this week. Hopefully, you're all doing okay with those. Uh, and the other piece of logistics is about midterm. So I will post some instructions for the midterm. So, but the basic thing is midterm is going to be in class, in person. It will be a written exam, and my style of midterms is you'll be given like physical question papers, and then you write your answers on paper, and then you just give it back to me. So there is no online component or Canvas component. It's just a written exam. You are allowed one double-sided handwritten piece of note, like your but it's closed book, but you can have some notes. One page of double-sided notes is allowed, but it has to be handwritten. You cannot type it. So I'm very old-fashioned that way. And we will not allow laptops during the exam, but you can bring in a calculator if you need to do some calculations. And the questions will be such that you don't really need to do calculations. Even if you do calculations, you can just use a simple calculator. That should be good enough. Try to bring your like own paper. I will try to get some paper, but if you need a lot of paper, hopefully the question that I print out will have some place for you to write your answers. But if you need extra paper, it is advisable to get your own paper, but I will also have some paper in case you don't have it. And also make sure that you have a stapler to staple your answer before submitting it to me. And the syllabus of the exam is going to be basically everything before the midterm exam. So all the topics up to the start of the class this week, next week, which will probably end at around backpropagation, which is the topic of next class. That would be in the scope of the syllabus, but anything before the midterm exam is going to be in scope. And then I'll send out some additional instructions for that. All right. Any questions from last class? Uh, I I will I'm not gonna have like sample questions. I will kind of put out a list of topics that you must study or that are more important for you. But if I can, I'll see if I can like post some sample questions. But nothing really planned so far. Yeah. But what I would say is that my questions are not meant to be tricky questions. Like I don't want to kind of torture you in the exam. If you followed everything I've taught in class, like if you understand all the derivations that I've done and you understand all the theory that we've covered in class, you should be in good shape. So just study everything that we've covered in class, look at all the lecture notes, and now you're going to see that your scribe notes that you and your classmates have been doing are going to be very useful, right? So read the scribe notes and all the material that we provided in the class, look at all the homework problems, look at all the assignments that you've done so far. And if you just understand everything pretty well, you'll be in good shape. I might give you some sample questions on the mathematical aspects because we've covered quite a bit of linear algebra. We're going to look at a bit of multivariable calculus and optimization. So I might post some sample questions on that for you to practice. Right. Let's see. Yeah. Okay. So I think I've started recording, and then I think I talked about the study guide. So a study guide in the sense of like a list of topics and possibly a few mathematical questions that I think I will provide you. So if you don't get it by sometime mid next week, just ping me again in the Discord group and I'll do that. All right. If no more questions, I think let's get started with today's lecture. So I'm gonna share my screen and let me know if you can see my screen.
Yeah, we can see it.
Okay, thank you. And do you see this OneNote page?
Yeah.
All right, cool. Okay, very good. So what I'm going to do is I'm going to basically write like all the notes on this OneNote, and this allows me to also draw some math and diagrams, but I will try my best to write as clearly as possible, but let me know if you see something is not clear, let me know because I'm not used to this. I'm experimenting for the first time, I think, with this. So so this is like the OneNote for today's class. So we want to cover like 3 topics today. So we were supposed to start this last time, but we didn't get to. So we're going to talk about RBF networks, radial basis function networks. We're going to review some multivariable calculus. And the idea in multivariable calculus is that we basically want to understand matrix calculus. Kind of by multivariable calculus, I mean like basically matrix calculus, where basically you take derivatives of like, I'm going to say matrices with respect to matrices. That's the most general thing we're going to do. And the reason I can say matrices because you know that like kind of vectors and scalars are special cases of matrices, right? A scalar is nothing but a matrix with 1 row and 1 column, and then a vector is just a matrix with 1 column, right? So if you understand in general how to take derivatives of a matrix with respect to a matrix, we will understand how to do matrix calculus, and that's going to be very useful for the derivations that we need to understand the algorithms for various neural networks. And we'll start with an example of RBF network itself. Now, one thing I want to say here is that when I say derivative of matrix with respect to matrix, we are not going to go as far as like a 2D matrix derivative with respect to 2D matrix, because that's going to become a much more complicated object called a tensor. So we are not going to go that far, but eventually our final derivative would be at most 2-dimensional, and we'll get there. But that's probably that's probably the most complex type of derivative that you would need in machine learning, at least the ones that we are going to work with here. All right. And then we also want to talk about optimization. We're going to start with the basics of optimization. Uh, and next week, we're going to hopefully continue with specific optimization algorithms that are used full in machine learning, starting with gradient descent, stochastic gradient descent. So we're going to do SGD, which is stochastic gradient descent. We can talk about the momentum-based methods. And there are techniques such as steepest descent. We might talk about Newton's method, which is what is known as a second order method. So it's a bit more complicated. So we might see it, but the thing about like optimization in machine learning is that if you kind of understand stochastic gradient descent, that's usually takes you about 90% of all types of optimization that you need, with a bit of momentum and some other techniques like RMS prop. We rarely go into Newton's method in like fundamental machine learning or neural network design. It's more advanced research where you kind of might see second order methods, but we might just cover it for completion, just to kind of understand. And when I say second order, it means that to do the optimization, you need to actually compute the second derivative of your function that you're trying to optimize. Whereas SGD and steepest descent, these are first order methods, because here the only information that you need are the gradients or the first derivatives. And with that, you can find your optimal points for your functions. All right. Okay. So that's the topics, and we'll start with RBF networks. So hopefully everyone remembers from last class the universal approximation theorem. And we talked about kind of two variants of it. Like one is like, how do you kind of use a number of binary classifiers or hyperplanes to approximate an arbitrary polygonal shape, right? So that if you have like a hexagon, you can have 6 hyperplanes, and then by building these binary classifiers, you can build a network that recognizes points inside that. So if I maybe start drawing a bit, what we saw is that I can kind of build a classifier that would recognize points inside this network versus kind of points that are outside the network, right? And then the idea is that what you need is you need to kind of build these hyperplanes that correspond to each boundary, and then each of these hyperplanes is an individual perceptron, right? So you will have like 6 of these perceptrons, and you have your input, which is x, the vector x, and this connects to all these neurons. So here x is meant to be a d-dimensional vector, input vector, and this connects to all the neurons. And then you have another neuron, which is basically an AND of all these, right? This is meant to be like the AND, and we know how to implement an AND with perceptrons. So that's kind of, and then we talked about the universal approximation theorem for continuous functions, right? And then we kind of sketched the proof idea that if you have a sigmoidal neuron, then you can basically have a layer of infinite sigmoidal neurons. And if you kind of put them together, then kind of you have two neurons, like you need two sigmoid. Oh boy. Make sure if something doesn't, if you don't understand anything I'm writing, just let me know. Kind of, I need two sigmoid neurons that would simulate this pulse, right? Uh, a pulse like this, right? And then if you have an arbitrary function, right, then basically I can approximate all these with, you should think of these as like rectangular pulses, but even though my drawing is horrible, but I think you get the idea. But you can basically keep doing this, and then you can basically approximate up to arbitrary degree of accuracy. And so can anyone tell me what is the, so that means that mathematically we can approximate any continuous function with a summation possibly of sigmoid functions, right? There are some parameters here. And then if I have an arbitrary function f, then the theorem says that this is approximated by a sum of sigmoidal functions, right? And then I might have a height parameter alpha here. So can anyone tell me practically what is the problem with this theorem? Like if you want to realize uh, a real function with this technique, like practically what are some of the drawbacks of this approach? Anyone?
You might need a lot of neurons.
Exactly. The theorem holds when you have kind of possibly infinite neurons. So even if you have a single layer, uh, you might need, even if it's like a finite but really large number, that still can be computationally expensive. And you might be able to, yeah, go ahead, Pranav.
Oh, I was just gonna mention like it may not be good for non-continuous functions or
Hmm. Yeah, that's a good point. Uh, so drawbacks. One is kind of you might need infinite perceptrons. And then the other thing is that we might not have a continuous function. There are ways to deal with a non-continuous function. And the reason is that uh, basically if it's non-continuous, uh, if it's non-continuous, like even though the sigmoid is a continuous function, right? Uh, remember that we are kind of approximating these with discrete pulses, right? So if there are kind of some non-continuity there, uh, the problem might happen if you have something like this, right? So you kind of have a function that kind of goes to infinity here and kind of goes back to infinity here, right? And the problem here is that here the gradient at this point, or the differential, kind of the derivative of the function, let's say with respect to dx. This is infinity, right? And kind of the way to kind of deal with that is basically a kind of a simple trick is that as we are dealing with functions, like if you consider really arbitrary, crazy looking functions, there is no way you can learn anything, right? So the trick that machine learning folks do is that you kind of restrict the class of functions. And then if you have like such discontinuity, you can pose an extra regularity constraint such that your derivative is bounded, right? In that way, you kind of deal with functions that come up in machine learning or practical scenarios that have uh, bounded derivatives, and those are known as Lipschitz functions. And if you use them, then you can kind of deal with such non-continuity. And then the other thing is that even if you have some discontinuity, you can still model them with a finite approximation of these pulses. Okay, very good. All right, so that was kind of what we talked about last time. So now let's look at radial basis functions. So uh, so you can think of radial basis functions as a somewhat finite realization of the universal approximation theorem. Uh, so so in previous lectures, we looked at perceptron, which was a single neuron, right? And that has limited capabilities. And then the first kind of way of generalizing is to kind of think of a one layer of hidden neurons. And that's where we saw that the universal approximation theorem tells us that that's enough to model anything within some constraints. And then the RBF is an example realization of doing that. So let's kind of take a look at that. So let's see. Okay. So can you see my screen now? I have a
Yeah,
PDF open.
we can see it.
Okay, good. All right. So so I'm gonna like this is like a kind of a PDF that I have borrowed from another course which I'm going to use to kind of explain RBF networks, and I'll share my annotated notes after the class. But this picture would give you an idea of a radial basis function network. And then so there is a, again, just like most other neural networks like Hebbian learning perceptrons, there is a neuroscientific basis for radial basis functions. And I'm not going to delve too much into that, but kind of the radial basis functions in some sense model receptive fields of sensitivity in nervous systems. And that's all I'm going to say about that. If you're interested, I will share some details on that, but we're not going to delve too much into it, but we're going to think of it as a way of approximating the universal approximation theorem. Okay, so like this gives an example of a radial basis function, and the idea is like this. Okay, all right, right. So uh, we have uh, okay, so we have kind of an input vector. So it's an n-dimensional vector here, right? And then we have a bunch of special neurons here, and the neuron have these are annotated with this like bell-shaped curve, and we'll talk about why that is. But we have like, let's say, m intermediate neurons, and then finally we have an additive neuron here. We don't have any weights from the input to these hidden layer neurons, but we have these weights on the second layer from these hidden layer neurons into this final additive layer. So if y is the final output from this network, then y is a sum of the output of all these neurons. And we are saying that this neuron, first neuron output, is basically a function of the whole input x1. So you can see that all the x1, x2 up to xn, they're all connected to all these neurons. So this is basically what we call a fully connected layer. So R1 is a function of all the input inputs of this neural network, or just the input vector. So there, each Ri here is a function of the whole input vector. And then you take that function for I equal to 1 to m here. So this is I equal to 1 to m, where m is the number of hidden units. And then the sum is weighted by these weights on each of these lines. So the b1 is the weight for this first function, b2 is the weight for this second one, and then so on and so forth. All right. So that's kind of the architecture of a radial basis function. So if you compare with the universal approximation theorem, the differences are basically we are replacing a kind of a sigmoid neuron with this radial basis function neuron. And then we are also, because this is a finite approximation, we might only have a finite number of these radial basis functions, and then we are adding them up with some weights, right? And here, what are the trainable parameters of these functions? So first of all, these weights on these edges, these are parameters that we have to train, and that can be trained using a particular optimization formulation, or we can, as we will see in this class, that we can actually find an exact formulation to learn these parameters. All right. And then if you look here, so we actually have another set of parameters which we're calling the C parameters here, which are vectors. And where does this come from? And that comes from these radial basis functions. So what is the structure of these radial basis functions? So this gives a kind of a structure of the radial basis function. So the structure of the radial basis function is basically we have to find a center, and then we're looking at the distance of the input vector from a number of centers, right? And then once we have the distance, we use some sort of Gaussian or exponential function to kind of find a mapping from the input to a distance, such that if your input vector is close to one of these centers, and we'll look at a visualization in the next slide, then basically this neuron fires. And if it's far away, then it fires with a lower probability, or it doesn't fire at all, right? And then based on this, you can see that your input might belong to multiple classes, and then it fires based on which class it belongs to. Okay, so CI is a parameter that is basically, in some sense, a center of a particular receptive field, and then it fires when your input actually is close to that cluster of points, right? Okay, so let's see. I think we'll make it a bit clearer if we kind of go to the next slide. Okay, so let's see. Okay, so let's first look here. So think about this example, right? So basically we have a two-dimensional space. So our input has two dimensions, two components, x1 and x2. So we can draw it on a plane. And basically we have a nonlinear classification problem, right? So we have these red points in the center, and then we have the blue points near the outlier. And based on what you've learned so far, or thought about, you know that what we are trying to find here is kind of we want to find kind of a nonlinear boundary between these two kind of points, right? Uh, and then what do we want to have is, we notice that basically we have kind of this, at the center we have this cluster of red points, and we have at the outlier we have all these blue points. So if we find a point, a new point like this point, right, we want to classify it as this red point, right? And if we find a point that's kind of out here, then it should be a blue point, right? And then we can see that this green point, the distance to this green point to all these red points is much smaller than the distance to these blue points, right? So basically, if when we pass this new green point here to our radial basis function, we would want it to fire with a high intensity, right? So we would want it to kind of give a high value. And that means that we need a function that is going to give a high value when the distance between this green point and all these points is small. It would fire basically a receptive field for these red points.
Oh,
And then,
excuse me.
yeah,
Um, is it okay if you use a different color instead of like red and green? Because I have a type of color blindness that makes it kind of hard to differentiate between those two.
okay.
Yeah,
I'll
thank
I'll
you.
I'll try my best. What color works for you?
Oh, you can just change like either green or red. It doesn't really matter too much. Just that combination's a little hard to work with for me.
Okay. So let's use black if that's okay.
Yeah, that's better. Thank you.
All right. So this is our classification boundary, and then we have these test points. So this test point that is close to this red cluster of points, uh, we want that to fire. Basically, if you look here, uh, what we're doing, basically we know that we have this cluster of points here, and we want to find the centroid of this cluster of points, and then we need a function that kind of maps takes any point, and then if it's close to this cluster, it will output a high value, which is why we have this bell-shaped curve, which is a function that would take as input the distance of the point to any centroid. And if the distance is small, it would fire. But if it's small, then it kind of smooths out and you have a low intensity, right? So that's kind of the idea of this. Uh, and now, so then that happens for the cluster in the middle. But now what about these points in the outliers? Kind of what we have, these kind of outlier points, which are kind of blue here. Uh, uh, so like uh, kind of kind of if you look here, these are uh, these blue points which I'm overwriting with black. So this is class 2 here, right? So now you can see that for the blue class, you don't really see like a kind of a concentrated cluster of points, right? So what can we do here? What we can do here is that we can kind of break this into like multiple clusters, and you can say that, okay, I have this one cluster here, which has, so basically I'm building a receptive field of this cluster of points, and then maybe I have another one here, and then maybe another one here, and then maybe another one here, and another one here, something like this, and then another one here, right? And then if you have a like a new, let's say a new point comes in like this one here, right? And then the receptive field or the function or the radial basis function would fire for this cluster of points. So we basically we're going to have like a neuron, a separate neuron for all these clusters, right? And they will correspond to a neuron in the hidden, one neuron in the hidden layer. And then depending on your, basically depending on your data, how complex your data is, you can actually decide how many clusters you want, right? So basically we're gonna use, there are many ways to do this clustering, but you can think of from machine learning a basic method like k-means clustering, where you can have a specific value of k and you kind of build a number of clusters, and that would give you this clustering. So now you have basically the clustering would give you kind of a centroid for every cluster, right? And then if you think of that, now each of these neurons would correspond to one of those clusters. And then let's say this R1 is the cluster corresponding to this middle sector, right? Then if you have an input that is close to the middle cluster, then this one would fire, and then we would have a high weight for B1, but the other neurons here would correspond to these outer classes, and they would actually get a small value. So then the output Y would be dominated by this upper neuron, which is the middle class, right? But then everything else would have a small weight. So that's how you kind of classify that if an input is in the if an input is in this middle layer, then that's going to correspond to the, in this case, class 1. But if you have an input pattern corresponding to any of these outer clusters, then depending on which one of these are going to fire and have a high value, and that would also get a very high value of this weight B, right? And then, so that's how you do classification in a nonlinear case here. Okay, so now let's look at, so now we understand that what we need is that if you have a point that is close to any particular cluster, then only that cluster would output a high value, but every other cluster would output a low value, right? So what type of function would that be useful for? And the basic function that we know is kind of a function of a normal distribution, which is kind of this bell curve, right? So how does this bell curve work? So you can see that you basically here you have a mu, which is kind of the cluster center, and then you have x, which is an arbitrary input. And now the bell-shaped curve tells us that if x is kind of near the center or close to the center, right, then you have a high value of the function, but as it moves further away from the center, the values diminish, right? And then if you plot basically x minus mu square, right, and then if you plot this on the x-axis and on the y-axis plot this normal distribution function, you will see that this decay is exponentially, right? Because basically it's an exponential decay function, as you can see here, right? So this is an exponential decay, right? You have this x minus mu square by a sigma square and a minus, right? So basically it's a e to the power minus x square, which kind of goes to 0 as x tends to infinity. Okay, so that's the idea of a radial basis function. All right. Okay. All right. Any questions so far?
So I have one question.
Yeah.
So for the actual classification, what would the output look like for like class 1 versus class 2?
Right. So eventually, after you basically, so now that's a good question. So what would happen is that, uh, right. So if you look here, right. So what we're gonna do is if you do a binary classification, then the way you kind of design the network is for the positive class, you would do like a, a kind of a normal bell-shaped curve, and for a negative, for the outer class, in this case the zero or negative class, you kind of flip this output, right? uh, so the way you would do that is basically, if you look here, right, as you're learning the weights, basically, if the first class here corresponds to this inner layer, then that would have like a positive weight or a strong positive weight. But if you have any of the other classes, then B2 would have kind of in some sense a negative weight, right? And the negative weight would kind of flip this receptive field. And then if you and you can design the network such that basically for the inner class, your output is going to be positive, and then for the outer class, your output will be negative, so that you can basically have a rule such that at the end, if you get ym, right, then if ym is greater than 0 or some threshold, then you say that it's the positive class, and if it's less than a threshold, it's the negative class, right? So that's kind of the idea. And then you can also have, if you want, you can have a bias term here, and then if the output is greater than the bias, then you say it's positive, and if it's less than the bias, you say it's negative, right? So at this point, this is still a continuous output, but then you can use some existing techniques where you have a threshold, and then basically you pass it through a threshold, and then if it's above some threshold, you say it's one class, and if it's below a threshold, it's another class. So that's how you actually make this into a classifier. But it in general, it would also work for a continuous function, right? Where you kind of basically, instead of classification, if you want to do regression, you can use the same network for regression, but you just use the actual value y as your regression output. But if it's classification, then you have to add a threshold here or some sort of probability function, right? Basically, what you can do at the end of here is kind of pass this through kind of a what do we call? So basically, this is ym, right? So you do like, you can do e to the power ym 1 plus e to the power ym, right? And then the other value is going to be 1 divided by 1 plus e to the power minus ym. And this becomes your probability, right? This becomes kind of your probability of, let's say, plus 1, and this becomes your probability of minus 1. And then basically you took to the majority, right? Whichever one is bigger, then you say it's class 1 or class minus 1. Right? Good question. Does that answer your question?
It does, thank you.
All right, cool. All right. So now let's try to kind of mathematically formulate the radial basis function. We understand the architecture and kind of the intuition of why it works. So now let's try to kind of basically my goal is to show that we can actually find a closed form expression for this radial basis function. So hopefully I can find my notes. Okay. All right. So let's go back to our board here. So let's kind of try to draw out a radial basis function. So we had this, I'm going to say I have this, doesn't matter the input dimension, but let's say it's a d-dimensional vector, RD. And then this goes into a number of neurons, and I'm going to represent the neurons by like a radial basis function. And I'm going to say it's like we have the function phi1, which corresponds to the first radial basis function, right? And then I have another one, which is phi2. And then I have, let's say I have m of these radial basis functions. So this is the mth radial basis function, right? And then this becomes like, these are my single layer of neurons, right? These are my single layer of neurons, and this is my input. And this is maybe I'll make this a bit clearer by drawing them as x1, x2, x3, xd, right? And then basically we have a fully connected layer here. Okay. And then finally we have this kind of additive neuron, which just takes all these and adds them up, right? And then here we have these, we're going to have some weight values here, right? And in general, we are going to actually have a number of output layers here, right? And the number of output layers basically means that we have a vector valued output, and that is fine. So then these are all going to be connected to all these output layers. And so again, this is also a fully connected layer, but there is just one hidden layer, right? This is the only hidden layer. So one layer of neurons, and these are just additive units. So there is no kind of nonlinear function or a radial basis function here, right? And then this is my output. Let's say my output, I'm going to say y12, yk. What is my dimension of, let's see, what did I want j to go to? Y. So I'm going to have m, and this is going to be n. So I'm going to have, this is y1, the output. This is y2. This output is y3, and this output is yn, right? So I have my input vector, which lives in a d-dimensional vector space, and my output vector y lives in a n-dimensional vector space. Okay. So far, so good. All right. So now So this is my general setup. And then when we are kind of analyzing the network, we are going to assume that we have a given known form of these five functions, right? And if you recall from my diagram here, this is usually can be a normal distribution, right? And like any function of the distance between a point and a cluster is gonna work here. Kind of another way to think about this is like, how many of you are familiar with what a Fourier series is? You should kind of probably know it from any applied math course. Anyone heard of the Fourier transform, Fourier decomposition?
Does it break down like a wave into smaller waves?
Exactly. Basically, any complex wave. Now, what is a wave here? For us, a wave is a function, right? So it's a function, like it could be some really complex function, right? But what it says that we can always break it down into kind of this first component, and then we have a higher component, and then maybe a much higher component, right? So basically, your any function is kind of a summation of these kind of sine, maybe of nx plus cosines, right? Where n describes kind of the nth order frequency. But the idea is that you can decompose any function in terms of simpler functions that are, easier to analyze. And now there is a kind of analogy between these radial basis functions and these sine and cosine functions. And the reason for that is you can think of a sine and cosine, and then there is a way to kind of also write this as a sum of exponents, right? This can also be like thought of as kind of e to the power some I n x, right? And then this now becomes very close to the radial basis function, right? So there is a mathematical justification for why this would work. So that's kind of an analogy of why this would work. All right. Okay. So now let's get back to our. So now this is the setup for us. So now, how can we write each of these yi's mathematically in terms of this representation? Okay. Can anyone suggest? Like, now I want to basically write down a equation for yj in terms of this network. What is a, let's start with, let's say just y1, or I think it's okay. We can just use yj. It should be okay. So how can I write yj in terms of these functions and these input vectors? I also need to specify, uh, so I'm going to give some weights vectors here. So this is y11, this is y12, and then for example, the last one is w. So this is the first index of w is from the basis function, and the second input, second parameter is the output dimension. So this should be ym n. All right. So we have all these fully connected layer of weights. And now how would you write yj in terms of all these parameters here? Any guess?
Would it just be like a linear combination of the radial functions and all the weights?
Exactly. That's absolutely correct. So basically we're gonna, so we can write it. let's first write it down. So basically what would be yj, and let's call it a yj hat because it's our expected output and not the actual output. So this would be basically this is the jth output, right? So for all of these we're going to have the second parameter would be always j, and then we're going to have the first parameter go from 1 to m because we have m radial basis functions. So this would gonna be like w 1j, and this would be the first function. And what would be the input to this function?
The vector of inputs.
The vector of inputs, exactly. So this would be basically this gonna be basically the vector x, which is the d-dimensional vector. Very good. And then this would be the second, wait for the second function, phi 2 x bar, and then we keep going until we get to the mth one. So this would be m j phi m, and that would be my yj, right? So to give a smaller example, let's say we have a system where I have basically, let's example where I have 2D inputs, right? And then my output is also two-dimensional. And let's say I also have m equal to 2, right? So that's kind of a simple system. So in that case, I would just have two equations. Y1 hat is going to be W1 1 by 1 of x plus W2 1 phi 2 of x and then I'm going to have y2 hat equal to w1 2 phi, sorry, phi 1 of x plus w2 2 phi 2 of x, right? And now what I can do is that I can now kind of think of kind of transforming this into a matrix equation. So I'm gonna use this example and then we can generalize, but this would be a vector of the output, right? And then we're gonna have a matrix here, which would be the weight vectors. And then here I'm gonna have phi 1 of x and phi 2 of x. All right. And now we're going to have some weights here. So that if you just translate from here, what are the weights? You're going to have W11, W21, W12, and W22, right? And now, if you think about this, if I call this kind of a, yeah, go ahead, Pranav.
Could you remind me why, for the weights matrix, like the rows, like the way they're indexed, like it's 1 1 and then 1 2.
Right.
Yeah.
It's again, it's a convention that here the first dimension of my weight vector, my weight matrix is basically coming from the radial basis function layer, and the second one is the output layer. But what we are going to basically do is that it doesn't really matter because I'm going to transpose the weight matrix, right? So what I'm going to say is that I'm going to think of a weight matrix W in this case as basically W11 and W12 and W21 and W22. So I'm going to define my weight matrix like this, right? And then I'm going to say that my output vector y bar is going to be this matrix W transpose times P of my input vector. Does that make sense?
Okay, yeah. Thank you.
Okay. You're going to see this, like sometimes you have W, sometimes you have to do transpose. The thing that matters is that we actually need to make sure that this, for example, this is now a matrix vector equation, right? We just need to make sure that the dimensions make sense, right? And now in this case, this is a square matrix, right? So we don't have to worry. But in general, like what we're going to have, so I hope this derivation makes it clear to you how we can generalize to this arbitrary dimension where in general, the input dimension, the number of neurons here, and the number of output layers are all different numbers, right? So what we're going to have is in general, your x, what 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 we are eventually going to do is we're going to have, so this, so like let's actually look at this in a bit more carefully. First of all, let's look at this layer here. So I have phi 1 of, actually this is bar, so this is a vector, right? Uh, this actually is going to be phi 1. You can think of it as x1 and x2, and then phi 2 of vector is phi 2 of x1 sorry, this is, yeah, so this should be, this is phi 1, and then we have phi 2 of x2. So this is the most general form of it, and then this actually becomes a vector like this. So that's how you would in general think of this. In this case, this is going to be a single number. Okay. All right. Okay, so let's look at the general form of this. So now I'm gonna like fully generalize this. So bear with me. So now let's think about kind of learning, the general learning process. Okay, so now what do we have to learn here? When we talk about learning, what are we trying to learn here? Anyone can anyone say what are we trying to learn here?
The weights between
Wait.
The weights, exactly. Very good. So we are going to be given a number of input patterns, which are a number of input vectors, and we are going to have like some target values, which would be y1 to yn, right? So actually, I am going to change this just to make it uh, clear. The output dimension, I want to actually make it this, I want to be k. So I'm going to make this k dimensional output. Else, sorry for the confusion. Okay, so that's going to be, so now I basically need to learn a corresponding weight matrix, right? And so you're going to see that once the design, the choice of the phi1, the structure of these radial basis functions, that's something is going to be given as a prior, right? So I need to know before I am trying to learn the network, I'm gonna specify as the structure of the network, what is my form of the radial basis function. So given any input vector x, I should be able to compute this. So that's not part of the learning. The part of the learning is learning these weight vectors, right? The other part of the learning is learning the centroid of the clusters, but that would be a pre-processing step where I run some sort of k-means clustering to kind of find the center weights, and then I'm going to feed in those weights as part of the radial basis function to kind of be able to compute for a given x the value of radial basis functions, right? So the learning eventually is going to be finding a value of these weights, right? And then you can start to think about what we are trying to do. We are trying to see if you can analytically solve this, right? Because if you look here, trying to find this weight vector is kind of some sort of inverse process where I try to invert this equation to kind of find a value of this weight matrix. That's eventually, in a sense, what we're trying to do here. And we'll see that. So learning is basically kind of finding kind of weight, the W, right? We're trying to learn a good approximation of this weight vector. Okay, so now let's specify in full generality our matrix equation. So we have a input vector x which belongs to d-dimensional space, right? We're gonna have m basis functions, our output function is k-dimensional, and I have n data sets. Okay, so I'm going to form a number of matrices. So the let's first look at this phi matrix, and then this is going to be living in the space of R M by N. So what this is going to look like, we're going to apply the first basis function on the first input vector. Okay, and then I'm going to apply the, sorry, again the first basis function I'm going to apply towards the second input vector. And then finally, I'm going to apply the first to the nth vector. And then I'm going to apply the mth radial basis function to all the input vectors. This is going to be M applied to the nth vector. And now hope this is clear that the dimensions are okay, right? So they have M rows for M basis functions and N columns for each input vector in my data set. And now if you look at the weight function, the first dimension is the number of Radial basis functions, and the second dimension is the number of output components. So my weight vector W should be in the space of R. M is the number of dimensions, number of Radial basis functions, and then the output is going to be the number of number of outputs, which is K. So that should be my weight vector. So now if I write it down, it should be something like this: W11 up to W1K, and this could go to WM1, WMK, and then this dimension should be easy to understand. Okay, we are doing pretty bad with time, but let me try to finish this. We might have to kind of do some slow up later on. But now I'm also going to have a matrix for the output. So I'm going to call this Y hat. And this is going to live in the space R. K is the number of output components. And then basically we have K outputs for all possible input vectors. And the input vector is n dimensional, right? So basically, sorry, we have n input vectors. So we're going to have one such vector of outputs for every input. And that's going to be why this is going to be a K by N vector. And this is what this should look like. We're going to have Y1, 1. So basically what I'm going to do is that my first column is going to be the output of the network for my first input vector, right? So that's going to be Y1 to YK, and 1 is the indexing the first input data set. So you can see this is the column index, and this is the n data sets. And this is going to be for the nth input vector, this is going to be the corresponding output. So this is all going to be K n. Okay. And now let's look at, so now we're going to have basically a generalization of this type of a matrix equation. And you can actually read it off by just matching the dimensions, right? So if I do this, I have W transpose and this matrix phi, and then I have Y here. So let's see if this makes sense. So what is the dimension of W transpose? Anyone? W is
K
M
by
by K.
M.
W is M by K. So W transpose should be
K
can you,
by
can,
M.
K by M, exactly. So K by M, and let's check phi. the phi matrix is m by n. So far so good. Okay, and now if we take this, then y bar has to be k by n, and we see that voila, that's actually correct. So we have the correct matrix formulation for our radial basis function. Okay, and now our job is to kind of estimate this matrix, and that would mean we've kind of learned our network. Okay, so that's our goal. All right, and now so we can see that we actually have another matrix in the picture. So what are we doing here? We are subjecting this network to a bunch of input vectors, and we find these output values, right? So these are actually the estimated values. But in a learning task, for every input, we would also be given a target output vector, right? So our data is a bunch of these vectors. So this is the first vector, and we would also have a corresponding output vector, right? And then we have this up to xn, right? That's my data. And then these, I can form another matrix, which has the same dimension as y, but these are the actual target values which belong to the same dimension, right? K by n. And now we're gonna try to learn these parameters. So how can we do that? So now we're gonna formulate this as kind of a minimization problem. What we are trying to do is that we have our target. This is our target, right? This is my target. And what I'm learning, what I'm outputting from the network is my estimate, right? So what do we want to do? What type of parameters W do we want to learn? And what is our objective? Like, what are we trying to, why are we trying to tune the weights in this case? Like, how do we know that we have a good value of weights in the context of this target matrix W and our estimated matrix output matrix y hat? My target y and the estimate y hat. Like, if you learn a good weight matrix, then what should it correspond to in terms of these target and estimates? Like, I hope my question makes sense. Like, how would you tune the parameters? What is the objective here? You're trying to learn by providing some input patterns and getting an output, right? So if your input has this vector and this is your corresponding y, right? This is your data, and then you run this through your radial basis function, and this outputs the vector y hat. When do you know that you've able to solve this learning problem?
When y hat is close enough to y.
Exactly. So the distance in some sense between y hat and y1 needs to be small, right? So that's our objective. So basically we can frame this as a minimization problem, right? And we are gonna talk about optimization like probably next class, but basically I want to find this weight matrix W such that a distance between the y, which is the target, and y hat, right, is minimized. And now if you look here, what is y and y hat? These are both matrices. So now we actually need a norm for matrices, and we learned that this norm is the Frobenius norm, right? So that's what we are going to try to minimize. So we want to find a weight such that this is minimized, and then we are going to basically square this, because a square function is always easily optimizable, right? Basically, the idea is that if you look at a scalar case, then if y equal to x squared, then what does this look like? This looks like basically a what we call a convex function, and then it's easier to optimize this. Convex functions are the easiest to optimize, and we'll talk about that possibly next class or next week. But basically, that's why we square this. But now, if we just write this down, what is y hat? Y hat is this equation, right? So we're going to plug in that here. So we're going to have y minus y transpose and the matrix phi, and that's what we want to minimize. Okay, so now we're going to do some calculus, and we might talk about more about the basis later class, but basically the idea of optimizing this is basically we have this function here, right? We have this function, and this is a function that includes matrices, but eventually we have a norm, right? So basically we have a real quantity, but the function is the parameter of the function. Y is a matrix of constant values. Phi is also constant because phi is basically we are taking all these input vectors and computing this phi on all of them, right? Uh, and then so basically these are also known quantities. So this is again going to be a constant based on the input data set. The only variable here is W. So we want to find a matrix W such that this term is minimized. And the way you do that is now, uh, if we call this as a function of W, right? So my goal is to minimize this function W with respect to function of W with respect to W. And now, can someone tell me what is the what is the input of this function? This function depends on W, and what is the dimension of this function output? Like this function spits out an output. What type of quantity is that? Like, is it a matrix vector or something else?
Scalar?
It's a scalar. So this is basically going to be just a real number, right? And then we need to optimize with respect to W, right? And W is a matrix, right? And we know the dimension of W is M by K. Okay. And if you remember some calculus, and we will kind of review that, not today possibly, but basically if you have a function X, let's say function of X equal to X squared, the way you minimize is that you kind of compute the derivative of this with respect to d of x, which in this case is going to be 2 times x, and you set that equal to 0. And now you know that x equal to 0 is a minima of this function, right? That's when this kind of x is basically a scalar. And we have to do exactly the same thing here. But now you see that the output is a real number, but the input is a matrix. So now, in this case, if I compute this derivative of this function with respect to W, this also is going to be a matrix. Okay. So that's why we need to understand taking derivatives of arbitrary matrices with respect to matrix, because in this case we have to take a derivative of a scalar with respect to a matrix, and that object is also another matrix. Okay. So now let's kind of try to. So I know we didn't take a break, but I think I'll just try to finish this and kind of we can end this. We just gonna finish the RBF network and we're gonna start calculus optimization next class. So just bear with me. So let's try to finish this. Hopefully that's okay. So our objective is to kind of now we want to do the same thing that we do in the scalar case, but for this more general situation. And now let's recall what we are trying to do here. So this is what we are trying to minimize. So let's look at this this quantity here, and let's see how we can massage it a bit. So we have y minus w transpose and a phi, right? And this the objects inside this norm are all matrices. And now this is a norm square, right? And any norm square I can write as a inner product, right? But in this case, if you recall, for two matrices, if you look at the notes, this is defined as a trace of X transpose of Y, right? And then if I do an inner product with X with itself, this is basically trace of X transpose X. And this thing is basically the Frobenius norm of this matrix F square. And then if I do the same thing here, if you kind of look at this, right? If you kind of, so basically this is the same. And if I kind of try to apply this to here, what will I get? I'm gonna basically get trace of Y minus W transpose phi, this object transposed with the same thing, Y minus W transpose phi, and this whole thing is within the trace. Okay. And now let's kind of continue along with this, right? So I can write this as, now let's kind of do some calculations here. So this is Y, I have a transpose and I have a Y here, right? So this is going to be Y transpose Y, okay? Then minus, I have this in a, and I'm going to transpose this whole thing. When you do A, B transpose, you get B transpose A transpose. So if you do that, what you're gonna get is this is gonna be phi transpose, and then W transpose is W And then we have the y here. Okay. And then minus this term and this term. So this is going to be y w transpose phi. And then finally, I take this term and this term. There is a minus and minus, so it's going to be plus. If I take the transpose of this, I get phi transpose w transpose, and then I have a phi here. Okay. And then I can take the trace separately on each of these matrices. So this will be y transpose y minus. And now let's look at what we have here. So we have basically, when we take a trace, this and this are going to end up being the same quantity because they're inside the trace. So let's look at the y. So I'm going to take the transpose of these two. I can break down. The transpose is kind of additive, so this is going to be the same. And then I have transpose of y w transpose phi. And then finally, I have transpose of phi transpose w transpose phi. Okay. All right. So now let's look at these two terms, right? So one property of transpose is, sorry, trace. So my apologies. There is trace and there is transpose. Hope that's clear. If you're confused, then let me know. This is the transpose operation, and this is we're taking the trace of this matrix, right? So sorry if I confused you. But what we're trying to do is we're trying to simplify this before we actually differentiate this. That way we will have a cleaner expression after we differentiate it. But now, if you recall, we had a property of the trace is that if you take the trace of, let's say, A, B, and C, right? I can cyclically move around these matrices and I have the same trace, right? So I can move B and C to the first, and then I can take A to the back. And this is also the same as trace of C, A, and B. Okay, so now let's apply this to here, right? So what are we gonna get? So this one, this should be a transpose here. Made a mistake there. So this should be transpose, okay? So now let's look at this term, trace of phi transpose W y. And now if you take the trace of a transpose of a matrix, right? This is going to be the same as the transpose of A. Can anyone tell me why this is true?
Because when you transpose, the diagonal is the same.
Exactly, the diagonal is preserved, right? That's why this is true. So that means this I can write as trace of phi transpose y this whole thing transpose. And then if I apply the transpose or multiplication, I'm going to get y transpose w transpose, and phi transpose transpose is basically phi, right? And now look at this. We started with this term over here, and then we got exactly this same term over here. So that means this term over here and this term over here are equal. Okay, so far so good. So now I can write my so this is my function of the weight w. So my final objective function is going to be what I'm trying to optimize, is equal to, my first term is, this is the first term. So that is trace of y transpose y. And then I have two equal terms. So that will be minus trace of it's this term here. Either of these is fine. So let's just write it as y transpose w transpose phi. And then we're gonna place 2 in front of it because they're both equal. And then finally, I have a term trace of phi w transpose phi. Okay. All right. So that's my final function. Uh, so now let's massage this a bit more. So basically, I'm gonna move around these a bit. So this term becomes I can do trace and I can cyclically move around these. So what I want to do is I'm gonna let's see here. I have, so this should be transpose. So what I want to do is I'm gonna move this to the front. So this is gonna be phi transpose weight matrix w transpose. And then I can do the cyclic rule one more time. And then I want to move this to the start. So this would be W transpose phi transpose W. Okay. And then let's call this a matrix X just for convenience. So now my function is trace of W transpose Y minus 2 times trace of. So here again, I can just move around this a bit more, right? And then for this term, I can again move this multiple times, and I'm gonna get this can be phi Y transpose W transpose, but W transpose I can move again here. So this would be like this. And then this would be plus trace of W transpose, and then we're calling this phi transpose as X and W. Okay, now we want to find D of F with respect to D of W. And now, as I mentioned in class, the trick here is to kind of think of all these as scalars and then find the scalar derivative and then think back about matrices, right? So now, like if you think of these as scalars, let's now think that everything is a scalar, like F is a scalar, we already know W is also a scalar, everything is a scalar. So if I want to differentiate F with respect to W, this first term, what is the derivative of this first term with respect to W?
0.
0, exactly. Okay, minus 2 times. So now I have a trace of, basically trace of something with W, and then with respect to W, this part is constant. Okay, so it's kind of like a function of X equal to, in some sense, A of X. So if I differentiate now trace of this function with respect to W, kind of what would you expect to get? So it's like this is the variable part and this is the constant part. And then you differentiate with respect to this variable, you expect to kind of get something that is just proportional to or equal to these two matrices, which are kind of the constant values, right? So it's going to be some order of Y, P, Y, and or Y transpose. But now what we need to do is we need to make sure that the dimensions are okay. So the way we are going to do that is we know the dimension of this has to be the same as the dimension of this function f, and we checked earlier that the dimension of this is m by k. Okay, so now let's write it down. The dimension of this has to be m by k, and then that means this whole thing has to be m by k. And now let's check the dimensions of phi. What is the dimension of phi? If you look back, phi is m by n, right? So far so good. M,
Do we
go ahead.
not do anything with the trace of W transpose X W?
This one?
Yeah, does that not factor into the
Yeah, we're getting to that. So first we are doing this, and we're getting to that.
Alright.
We're now working with this term. So we're gonna get to that. I'm just going slowly. So far we have that this is 0, and this is going to be, so we downgraded them to scalar just for our benefit, and then we saw that this is going to be this variable times these constant matrices, and now we think back from scalar to matrix, but now as we are multiplying these, we need to make sure that the matrix multiplication makes sense, and we also have a constant that the dimension of phi and y has to match the dimension of this thing. So we're just trying to make sure that we have the right order and possibly the right transpose of these two things. So phi has dimension m by n. And now what is the dimension of y? Can anyone tell me? Y is k by n. Okay. So y is k by n. But now phi times y, we cannot multiply because phi, this don't match, right? N and k don't match. So what can we do here to make it match?
Transpose y.
Exactly. We just transpose y and then this makes sense. Very good. So now we have a proper matrix for this one. And now let's look at this one. Again, we're going to do the same thing. We're going to consider w and x to be scalars. So if w and x become scalars, then this w transpose x w, if they're all scalars, then the order doesn't matter. This becomes something like w square x. And then if you differentiate this, the scalar, what becomes the value here? As a scalar, you're differentiating, basically this is kind of here, x is the constant and w is the variable. So differentiate this with respect to w gives you what?
2xw.
Exactly. So 2xw.
And quick question. Why do we simplify it to w squared from w to xw?
Because the kind of the dirty trick here, and we'll do a more rigorous way of this in next class, but the what we are saying is that these are, when we are trying to differentiate, we are differentiating the trace of matrices with respect to a matrix. The rule for that is complicated. So for now, we are first thinking that we are going to think of them as scalars. And as scalars, if w and x are scalars, then the matrix order doesn't matter because scalars are commutative, which
Okay.
is why, and also as transpose of a scalar is also the same scalar. So w transpose becomes, in terms of scalars, wxw, and then now you can commute this thing, and this becomes two w's together and an x. And then as a scalar, if you differentiate, you get 2xw. But now we are going to elevate them back to matrices, right? So let's write it back here. So now it's 2 times x times w. And now let's check the dimension of these matrices. So what is the dimension of x? What was x to start with? We said x was this matrix phi phi transpose. So let's write it down. Phi phi transpose. What is the dimension of phi? Let's go back. Phi had dimension m by n. N. And then phi transpose is n by m. So x has dimension m by m. And now let's check this quantity. So if this is m by m, and what is w? The dimension of w is m by k. So x times w would also be m by k. So I think we are good here. Okay. So now we've elevated them back to matrices, and now we have a proper matrix equation. And now finally our equation is, let me just check if I have everything correctly so that I don't mess it up. 2x phi y transpose. Okay, I'm good. So now I have my final equation. Now everything is back in matrices. So d function by dw is equal to, this is 0. Here we have 2 times phi times y transpose, and we have a minus sign, 2 times phi times y transpose. And then I have a plus. Plus, what do I have? It's 2 times x times w, but what was x? X was phi transpose, right? So this is actually a plus. So I have plus 2 times phi transpose times w. And the rule of calculus, if I want to minimize f, I need to set this to 0 and solve for w. So now this 2 and this 2 gonna cancel. And what do I have? I have, and then I can take this on the other side. So I'm gonna have phi transpose w equal to phi y transpose, right? And now to solve for y, what can I do? Can anyone suggest what to do?
Would
How do we
be
recover y from here?
multiplying by the inverse of phi transpose on both sides.
Exactly. If I do that, I get w equal to phi transpose inverse. And why is this inverse valid?
Uh, it's a square matrix since it's
Square
being
matrix,
multiplied by
exactly.
this.
And we know that basically if it's a square matrix, then we also need to make sure that it's invertible. And we looked at this in the previous class, right? Remember that if it's not invertible, we can add, basically we can do phi transpose and then add a kind of a lambda times I, and kind of take a very small lambda such that this thing gets invertible, right? That's the trick that we looked at last time, and we can do the same thing in this case if phi transpose number to be singular, right? So basically we add a small lambda and this diagonal matrix to make this invertible. And numerically, it doesn't matter to use this because this and this are almost the same. It's almost equivalent, right? But that this is going to be invertible. Okay. And then if you recall, this thing exactly looks like what? Do you remember what this expression looks like? We had a name for an expression like this. It is what we call the pseudo inverse, right? So basically, this is an expression for the pseudo inverse. All right. And now, if you look back at our original equation was basically, this was our original equation where is it? This one, right? Y equal to y transpose phi. So we had we are computing y equal to W transpose phi. And from here, if you check the dimensions, this is not a rectangular matrix, right? So we cannot really, from here, recover W in some sense, like kind of, we cannot do something like W equal to, what will we do here? Kind of Y phi inverse, right? Because phi is not rectangular. So we can't really do that. So eventually we have to do something, we have to actually take the pseudo inverse because our, uh, our, this would be something like, we take the transpose of this and do Y transpose. So we cannot directly take the inverse because phi is not a rectangular matrix, but we can do that by taking the pseudo inverse. And then basically this is now, so now we actually learned the network. We have actually a closed form solution, right? So this is kind of the closed form kind of learned weights for the RBF network. Okay. And basically the way you would learn this is basically you can compute, y is your y is the target output vector, and phi you can compute, and then all you have to do is kind of, you have to take the pseudo inverse and multiply by the transpose of the y matrix, and then you have learned the weights. So for your input data set, you can compute these two matrices, and then you just do this matrix calculation, and you have the learned weights, and that would give you the best weights for the RBF network. All right. So I think we can probably end here. So we have 2 minutes. Any questions on this so far?
So we just compute the weights once essentially, or is it a recurrent, or do we keep calculating better weights?
So this is not going to be an iterative process. What we did is that, and this is a special case for the RBF network because we found a closed form expression of the weights. So what we would do is that if we were doing some sort of iterative learning like gradient descent, we would kind of run it through, basically we would kind of run it through all the inputs and do weight iterations, or just like you do with perceptron. This is different where we basically have a one-shot computation to find the optimal weights.
Gotcha.
This is mathematically guaranteed to be optimal because the way we got this weight is by solving this optimization problem, right? This is y is the target y, and this is your computed y from the network. And we formulated this as a distance function, and we are trying to find the weights that minimizes this distance, which makes that estimated y as close as possible to target y. And then by doing this optimization, we found that the optimal value of the weight is this expression. So for a given set of input output vector pairs, all we have to do is like take all those vectors of inputs and outputs, and from that we compute this phi vector and this y vector, take the pseudo inverse, do this multiplication, and the weights that come out are guaranteed to be the best weights for that network. It's just a one-shot calculation. So this is rare. This only happens for a simpler one-layer network in this case, but in general, for multi-layer networks, you will have to learn the weights through iteration like backpropagation. But in this case, we are lucky and we have a closed form expression.
Got it. Thank you.
All right. All right. Cool. Any more questions?
I have a question about the homework assignment for Friday.
Okay. Sure. Sounds good. So if no more, are there any more questions about the lecture? Or are we good for now? All right, I'll take that as a yes. We're good for now. And so basically, just to summarize, we kind of discussed the RBF networks and we kind of did a very detailed calculation of finding the optimal weights for the RBF network. On this way, we kind of did some calculations which involved kind of optimization, taking derivatives. Some of these techniques we'll also cover in the next lecture on calculus and optimization. So we'll kind of fill in any gaps that we are missing today. And we'll look at we kind of cheated because we had to take a derivative of a scalar with respect to a matrix, and we cheated by saying that we're going to consider all of these as scalars, find the derivative with respect to scalars, and then elevate them back to matrices and make sure that the matrix dimensions match. But that's a quick and dirty way of getting this correctly done. But there is also a bit more rigorous way of doing that, and we will see that next class. And that's how we're going to close all the gaps. All right, so that's the end of the lecture. So now we can talk about any questions about the homework. Yeah, Onam, go ahead.
So, the backward function is supposed to take in a vector of errors, but for the perceptron learning rule, don't we need to also have the input to like add or subtract? So how do we go about that?
Let's see. Let's take a look at. So this is going to be this one, right? This is it, right? Is your question to some part of this question here?
Yeah, and question or part 2.
Okay.
Yeah, it says implement a backward method and it takes in a single argument, a vector of errors. But I thought we also needed to use the inputs for the learning rule.
Okay, let's check. Implement a backward method for the perceptron class. This methods. Right. Let's see. Right. So basically, what I'm trying to kind of do here is kind of make you think about generalizing this to more general learning, right? So if you see here this error loss function, what is this error loss? You have a activation A and a target T, right? So T is like your output label, and A is what you're computing in the network, right? So the error vector E is the difference, right? So the once you kind of do this backward with this error, right? So you are actually kind of somehow in some sense embedding your input inside this activation A. So there is no strict, I'm not going to be strict about the exact way you kind of implement this backward. So you can, if it makes it easier for you to kind of add an additional parameter, which is the input vector X, that is fine with me. This is like one way of doing that, but if you kind of also have additional parameters in the backward where you have a parameter for the X vector, you can certainly do that. That should be okay.
All right, thank you.
Does that answer your question? All right. I can understand, like, what I'm trying to do is kind of take the perceptron learning with in terms of, like, for example, W equal W plus X or W equal W minus X. And that's the way to implement it. But I also want to make sure that we can generalize from here to back propagation learning, which is kind of the next one, which is why I'm doing this. But if it makes it easier to kind of have a backward where you have a additional input parameter X, then that is fine. Because backward is where you're gonna kind of update the weights. So inside backward, you would have like W plus H W minus X. So it makes sense that if X is a parameter, then that makes it easier. So that's perfectly fine. Make sure you kind of write that in your comment that you're using an additional X parameter if you are not embedding x inside A, then you can explicitly have x as a parameter in your backward function. That's perfectly fine. But make sure you comment it out so that the grader knows what you're doing here.
So if we were to do it without adding an extra parameter, how would we adapt the learning rule to work off of just the error?
Right. So you would have to kind of think about so what is going to be t, right? So let's maybe look here. All right. So I have my target T and I have kind of A. A is kind of the in W minus X, right? So kind of this is probably W transpose X, and then your error is kind of, what do we say the error was? Error is T minus. So error is T minus W transpose X. Right, so that's what we're calling E here. Let's see. And then your kind of your backward function is a function of E. Right, so once you have a function like this where you have E, so I think you just need to kind of do some algebra here, but you kind of W new if it's W plus X, right? So from here, right, I believe there is a way to do this, but I might have to check the calculation.
Have,
Yeah, go ahead.
so with a backward function, would the backward function be within the perceptron, or is it something I'm doing outside of it, instead like of a main driver?
That depends on how you're implementing it. So basically, I would think that you would have like a perceptron class,
Yes.
right? And the perceptron class would have like it would have kind of a state of your weight vector. That would be a state, and then you would have like a it has a forward
Back.
function that takes as input a vector,
Yep.
and then a backward kind of. In this case, I think probably, as Anup was pointing out, it might be easier if this typically should be E, but it might be easier if you also pass in the X parameter here to run the backward.
So
Yeah. So it
yeah,
would
that's
be
why I'm asking, is if the backward function is just inside of forward, then I wouldn't need to do that, right? Because you would always want it to update if you're doing the perception learning rule based off of the error.
no, it should be separate. These should be two separate functions. That's how you
Okay.
design these things. Because if you want to extend it to like a multi-layer perceptron, kind of, you would have to kind of change this together. So you kind of have like from here, you kind of do a forward pass, right? And then from here, you do another forward. And then finally at here, you have this final loss function, right? Which will be like y minus y hat, right? And then eventually from here, you start doing the backward, right? And then a backward is going to be every neuron will have its own backward. And then this backward will kind of take as input the gradient from here and do its own backward, which is going to propagating the loss in the opposite direction. So each neuron should have a forward pass and a backward pass, which is why that should be the structure. So it should not be inside your forward.
Okay, so if I make it so my perceptrons keep track of their inputs
Mhm.
and outputs, then the backwards should work fine then.
Yeah, yeah.
Okay.
But right now we are just running with a single perceptron, so you have a single input. When you generalize it to multiple perceptron, then you would have think about the input to this perceptron is going to be the output of this perceptron. So you kind of model it that way. Going back to Anup's question, I'll double check. I believe I had a way of kind of making sure that you can have a perceptron rule for this, but to make your life easier, you just make X additional parameter. But I'll look at my notes and figure out what was the rule that I had in mind for this. But just to make it compatible with how I taught perceptron, you can have the X as a parameter of your backward. Or if you want, you can also replace E with the parameters that you want. So maybe you don't even need E because from here, the W is kind of a state of your perceptron, and then X is your passing also in backward. So with that, you can have the learning rule properly.
All right, thank you.
All right. Any more questions or anything about anything else in the class? I'll share the material that I had today after the class.
Thank you.
All right. All right. If nothing else, like I'll see you on Thursday. And if the class is in person, we'll see in class. Otherwise, when I hear from the university, I'll and if the classes are remote again, then we'll go remote. So I'll keep you posted.
Thank
All
you.
right.
Have a nice night.
Thank you.
Have a nice
See you
night.
Thursday, I hope.
Take care. Talk to
Thank
you on
you,
Thursday.
Professor.
Bye. Thank you. Thank you.